of bipod robots, as just mentioned before, we designed a new series parallel actuation concept as a symmetrical compliant actuation, which is short as ACA here, where it consists of two branches. So the first branch is branch short as PB, so which consists of SEA. So the second branch is energy storage branch short as ESB, which function as PEA. So later we will explain why we choose SEA as the actuator for the powerful branch. So the ESB unit will be equipped with energy storage element and driven by another secondary high efficiency motor for doing the pretension tuning. So as the right side image indicates, for single driving joint, symmetrical compliant actuation can be divided into configurations, namely monoarticulated and biarticulated configuration. So when we expand the single joint ACA concept to multi-joints, for instance, in our case, 3 Dolph leg in all pitch direction. So we come up with 3 distinct actuation configuration, which we will call it like SEA only, as the left side monoarticulated and biarticulated at the right side. So we would like to, through energy efficiency comparison between SEA only and mono and biarticulation, to verify the ACA concept. As you can see, the SEA only configuration is the traditional design without any energy storage branch, just as the common bipod robots do. So also through another comparison between mono and biarticulation, so we will try to investigate the effectiveness of this bio-inspired design, which we'll talk later, such as the performance for energy efficiency and even the explosive motion. So here we have to highlight and explain a little bit more about the biarticulation design and also its difference compared with the monoarticulation. So biarticulation is a bio-inspired design from the human biarticulated gastrocnemius muscles here. So compared to the traditional articulated design, where we put knee joint ESB and ankle joint ESB independently at thigh and calf part, biarticulation goes some new points in ankle joint ESB. So where the tendon spanning ankle and knee joint, so specifically speaking, the ESB for ankle joint actually originated from the back of thigh part, and then it will wrap around knee joint and finally inserts at the back of foot, just as the slides show here. So after we're talking about the actuation concept, let's start with the detailed body design. So for selecting the main joint actuators for E-leg, namely the trunk, knee, and ankle here, which is also the powerful branch actuator in ACA actuation concept. So we have to decide the actuation type. So in our application requirements, we would like to seek actuators for high torque output and physical compliance ability. And we're knowing that right now there are mainly 3 types of actuators for articulated robots, and just as Patrick mentioned before in this morning, namely the gear motor with high stiffness force torque sensor, the series elastic actuator, short as SEA, and the proprioceptive actuator. From my point of view, they all have pros and cons. It's just based on different robots application requirements. Different articulated robots were developed. So here we analyze the pros and cons for actually all these 3 actuation plans. It's just summarized in this table. And since in our application, we are more focused on the performance of physical compliance and high output torque density. So therefore, we select the series elastic actuation plan for the powerful branch. So briefly speaking, the E-leg is a 3 Dolph leg in pitch direction plan, just as mentioned. All the Dolphs are distributed in pitch direction on hip, knee, and ankle joint respectively. And the related size, self-weight, and loading are actually semi-anthropomorphic design. We are just trying to mimic the practical load situation of humanoid robots. So the actuator we utilize for powerful branch of the trunk, knee, and ankle joint is the orange type from IT3 robotics series, whose desired torque is around 127 Newton meter at maximum. This kind of tree robotics SEA, which I think is a really wonderful actuator platform based on SEA principle. As mentioned before, the E-leg robot is also equipped with two parallel elastic actuator, which is the PEA here, knee and ankle joint. It will function as the energy storage branch in ACA concept. So here, so this part is used for help the powerful branch to generate even more peak torque and store the energies for the energy efficiency enhancement. Here we will talk something about the detailed PEA unit design. Since before we have mentioned, we got 3 actuation configurations. So in the hardware level, we have to enable the ESP unit's rapid switching ability. So as you can check the left side figure, all the ESP units are designed independently as modulars, so that can be mount and dismount within 3 and 5 minutes. So the figure at the right side here describes the specific bungee and tendon route for the ESP units mounted on the leg body in all 3 actuation configurations. So now we are coming to the specific design details for ESP units, which are the novel points in the whole design and the core elements for making up mono and bi-articulation. In the following slides, we will introduce the details of these energy storage elements, such like the bungee stiffness selection and also the force sensing ball screw nut design. So according to the design requirements here for energy storage, we finally selected the rubber type elastic bungee because it's best high torque weight density compared to the pneumatic springs, the metal torsion springs, and the linear metal extension springs. So for the bungee stiffness selection, it just requires to meanwhile consider the geometric dimension, which is the pulley radius mounted on joints, as well as its default pretension. So this will finally contribute to the torque applied on knee and ankle joint. So as a result, the rest length and the diameter of the bungee are 2 dominant parameters. So often summarized in the table here. So consider the time limitation. I just don't make further explanation here. And by the way, the bungee we selected is an on-stock commercial product from a French company called Saddle Technique. And here, since the bungee we utilized, we spot it got a very obvious S shape, which we don't like. It just means the bungee got a very obvious nonlinearity. So we could not trust using the simple elongation of the bungee to achieve the accurate force feedback. Therefore, the ball screw nut for fixing the bungee is also designed with the strain gauge distribute on a cantilever beam. So the corresponding results, the strain gauge linearity and the FE analysis about this cantilever beam are presented here. So regard to the actuation mechanism for tuning the bungee pretension, we selected the method of using the brushless motor plus gearbox plus ball screw plan by considering the compact integration, small weight, and the large linear tuning range requirements. So as you can already notice the equation here, the required linear tuning force and its speed are actually inversely proportional. So after some very hard trade-off, we finally selected the corresponding tuning force and velocity configuration under this particular motor, gearhead, and the ball screw types, which is in design linear speed of 5 centimeters per second and generate a maximum like 2,500 linear force in ideal situation without considering the real transmission efficiency and the structure valid. Here we also would like to share a small tip for the ball screw nut design. So where the traditional one-side connection design cannot actually handle the linear force more than 1,000 newtons because of the twist moment here. So we changed the design like the dual side connection symmetrical Bose-Coulomb design, as the image shows here, can effectively solve this problem. So since the negative twist moment is balanced, so based on this, the knee joint is realized as the image at the right down corner side shows. So for ensuring the structural strength and large hollow shaft design, the spatial thin section bearing from Cadence Company is utilized here. So here is the first experiment to verify the ACA concept effectiveness. Here is in terms of energy efficiency. So we proceeded the same motion, namely the cyclic deep squat motion with 23 kilograms load for all three configurations. It's the SCA only configuration on the left side, the monoarticulate configuration in the middle, and the biarticulation on the right side. And we calculate the root mean square electrical power consumption during the whole motion, which is actually 33.1 watt for SCA only, 15.4 watt for mono, and the 13.2 watt for articulation. So here is some analysis. We achieved the 53% energy efficiency enhancement in mono articulation with respect to the traditional SCA only configuration, and even 60% improvement in biarticulation with respect to SCA only. And biarticulation is a little bit slightly more effective than monoarticulation. Meanwhile, we can also notice the torque decrease on knee joint powerful branch actuator, which is from 57 Newton meter reduced to 24 and 23 Newton meter respectively. Therefore, we can make a simple conclusion like the utilization of SAA concept, namely the mono and biarticulation, can actually effectively improve the energy efficiency and reduce the torque requirements on knee joint, which is actually the real energy saving front. So here we have to also say that the essential reason for the energy efficiency in biarticulation, even slightly bigger than the monoarticulation, is so the biarticulation allows to implement closer the gravity vector because it permits the coupling of the generate torque depending on more than one joint position, which is simply the thing like this. So the biarticulation allows the ankle joint involved in the coupling from the hardware level, rather than the monoarticulation only the knee joint works. Here, since in the previous experiment, there is no active PEA pretension tuning, so the second experiment is to verify the ESB unit active pretension tuning for energy efficiency. It is still the same deep cyclic squat motion under 23 kilograms load. We tuned the pretension of the bungee from 5 millimeter to 85 millimeter in 25 seconds, as the demo shows. Okay, and meanwhile, talking about the linear force on tuning, here. So meanwhile, talking about the linear force on ESB tuning mechanism, so we can notice that it can handle around 1200 Newton, the linear force, which is a quite high dynamic load that proving the ESB unit design effectiveness, especially in terms of the dual side connection symmetrical Bose-Coulomb design, as mentioned before. It proves its effectiveness for Bose-Coulomb valley transmission under the high payload. So here are some another analysis about the previous experiment. So here, first is the torque on knee joint. As the pink line indicates here, the SEA torque decreased a lot thanks to the help from the ESB bungee. As the blue line shows, the ESB torque increased. So naturally, the net torque remained the same as the black line shows, since the 23 kilograms load doesn't change. So second is the important energy efficiency. We can notice an obvious net power decrease when tuning the pretension, as the pink line shows. Also one point, the energy consumption from the ESG unit for tuning the bungee is quite small, as the blue line shows, thanks to the high gear ratio, which can be almost ignored. So this brings another power consumption decreased from 29.7 watt to 11 watt, namely another 63% improvement. So meanwhile, in this this experiment, the pretension here is actually manually set as a constant. So after I left IIT, my colleague Wesley Rosen also achieved a higher 70% enhancement by using some specific integrated control strategy for tuning the pretension. But the results are not detailed in my presentation here. So the third experiment is to verify the explosive jumping motion. So as you can check the demo here, so the leg is with 23 kilograms and 15 kilograms load respectively. So this will try to simulate the real humanoid robot situation with 2 arms and without. And currently, the maximum jumping height is actually the 21 centimeter in 15 kilograms as the SCA only jumping configuration. So in the left side, we can also notice, for instance, on the knee joint in mono articulations, the net peak torque achieved 151 Newton meter. As just we talked before, the main SCA generates its maximum desired 127 Newton meter in torque. And meanwhile, PEA also contributes another 24 Newton meter. So which can be said that the utilization of PEA on knee joint actually increase the peak torque output when we're trying to do explosive motion. And also finally, during the explosive jumping motion, so the compliant on actuation embedded in series elastic actuator, which is the compliant metal elements, brings physical sternness against huge impact when landing. So here we have to say that we didn't apply any integrated control strategy for control the landing motion. All the protection for the hardware is all contributed by the soft under actuation in the actuator, which I think is an ideal design method in terms of hardware for the shock absorption, just in case if you don't want to design any further complex controller. Be more specific, the compliant elements embedded inside the actuator is indeed a torsion spring bar, which can be described in the above section view. So the stiffness of it is around 4,000 Newton meter per radian. So under the condition of high impact, it will function as an under-actuated spring that can absorb shock and protects the gearbox and the motor after. So meanwhile, we have to admit that this kind of protection mechanism is actually passive, which you have no way to control it. So the good point of this is you don't have to apply any specific control strategy, but sometimes the low stiffness of this kind of torsion bar will somehow bring negative effect to the position accuracy and also the dynamic bandwise. So from the point of actuator design, it is still a performance priority trade-off. So here are some reference paper related to this work. So I'm just here to present the hardware design part. So my former colleague, Wesley Rosen, who is right now assistant professor at University of Twente, and Vishnu Dev Amar, who is right now a postdoc at IIT, they are more focused on the modeling and the control part. And thanks for their excellent work here. Just in case anyone who interested about this work and want to have a further understanding about its modeling, control, and optimization part, please have a look about the papers here. So about all the work I would like to share with you, maybe a little bit short. I apologize for this. And thank you guys for the listening.
Thank you very much, Zeyu.
You're welcome, yes.
Sorry, excuse me that I had some issues with my computer audio setup and I missed the welcome session. I'm very sorry for that.
It's okay, yes.
Okay, so are there any questions from the audience? Well, Zeyu, actually I quite like the compliance or the impact mitigation introduced by the new design, because in our experiments, indeed, we observed a huge impact forces, and sometimes these forces may break the motors or the fragile harmonics. Actually, in my presentation, a big focus which is about these aspects: how to protect the hardware properly while exploiting impacts. So yeah, thank you very much for your presentation and great design.
Okay, thank you, Yuquan. Thank you for the organization.
I had one question, if we have time.
Oh yeah, sure.
How did you do the trajectory and control design for the jumping? On slide 26 here, the trajectory is designed by hand, or you use some step signal?
Oh, yes, that's a good question. Here is the trajectory is designed by hand because the work here is more focused on try to verify the design effectiveness. So after I left IT, the two colleagues I talked before, they are trying to apply some specific control trajectory to this. Here is like all the data are raw and all the trajectory are tuned manually. It's something like this.
Okay, thank you. Nice presentation.
You're welcome.